Hello, let's do a few enthalpy practice problems. So there are two things, formation enthalpy and reaction enthalpy. So make sure you clearly see what the two are. So the first one is delta HF, the standard sign. The other one is delta H reaction. So the first one is per mole, the other one is not. So the formation enthalpy is given delta H, the standard sign, 1 atmospheric and 298 Kelvin. And that's the formation, right? And that has to be from existing elements. And it is for per 1 mole. So those are the more important things to pay attention, the sign and the units. So the delta H formation is kilojoules per mole. So make sure you understand that, right? So what's the example? Carbon solid, oxygen gas goes to carbon dioxide gas. So this one is minus 394 kilojoules per mole. So it's given for that, right? So look at the H2 gas, half of oxygen gas, gives you one water molecule liquid, that's minus 243 kilojoules per mole. Okay, so that's how it should look like. So the water one is actually 283, I think. That's okay, you can check the number. So carbon monoxide and oxygen reaction is CO2. Carbon monoxide is not an element, so that's not formation. That's a reaction enthalpy. So that's a fundamental difference. So you know how to recognize the two. A reactant goes to product is a delta H reaction. So it's not the elements going to the standard material. Okay, right. So let's do some examples, right? So calculate the reaction enthalpy. This says reaction enthalpy question. So not about the moles, right? So let's get this one, easy one. 2NO2 gas and oxygen gas goes to 2NO2 gas. So it's actually 2NO. Okay, now so the given is this one, NO production is NO, is the first reactant is NO. Okay, so I'll put a correction there. So 90 kilojoules per mole, and NO2 formation enthalpy is 33 kilojoules per mole. So look at the units again. So we know delta H formation reaction enthalpy is the total enthalpy of the product minus total enthalpy of the reactants. Plug it in. Products are NO2 twice and 33 times 2, and reactants are 90 times 2. So the difference is minus 114. That is kilojoules, no moles given, because there is more than 1 mole anyway, right? So that's how you do it. In the in the reaction, make sure you start with the NO, oxygen goes to NO2. Okay, right. Let's look at the second reaction. This is a harder one. So glucose, C6H12O6, 6 oxygen goes to 6 CO2 and 6 water. This is a delta H reaction again. This could be given as delta H combustion standard. So anyway, it's a reaction. Even formation is a reaction, right? So everything could be delta H reaction. Now, what is given delta H formation? For glucose, it's minus 1260 kilojoules per mole, and oxygen is element. There is no formation in it. And CO2 is 394 minus kilojoules per mole, and water liquid is actually, it should be let me check. It should be 280, let's see. Yes, 286 kilojoules per mole, right? So in the previous one, I think I had gas, so that's why, that's okay. So again, delta H reaction standard is total enthalpy of the product minus total enthalpy of the reactants. So recognize so do it like this way. So 6 carbon dioxide, 394 times 6, it's a product, and water 6, it's a product. Put it into the product side with the numbers. So 6 times of 394, sorry, so yeah, together, yes, 6 times of 394 and 6 times of 286 comes to that one. and glucose formation is minus 1260, and make sure brackets and signs are properly done, and then we should get here, let's check this number here. So you're getting 1676 kilojoules. This one actually you have 1 mole, so you can say kilojoules per mole glucose combustion, you can say that. But just make sure it's 1 mole or not in that case, right? So this combustion energy, we cannot really harvest that much. So when we eat glucose, or if we actually combust, we cannot harvest the whole thing, right? That's the calculated value. Anyway, so we will talk about another method. So you might be surprised if you see this one in a question. So the bond energy use, it's actually bond dissociation energy. So if you break a CC double bond, it takes 264 kilojoules per mole to chop it off. And if you break H to H bond, it takes 436 kilojoules per mole. C to H bond breaking will need 410 kilojoules per mole. It's basically how much energy needed to chop the bond away, right? Now let's look at this example. This is actually hydrogenation using palladium carbon into the ethene. Ethene goes to ethane, right? So I'm just marking the colors so you can see. This is a pi bond, and the metal soaks the hydrogen gas, and then it's called a cis addition. It kind of docks onto the pi bond from the bottom. So, but you just look at the number of bonds we break, one number of bonds we make, right? So the delta H of the formation kilojoules given 52 and minus 88. So you can also do the previously did normal reaction enthalpy calculation. So to see whether you get the same numbers, at least close enough, right? But for the bond dissociation energy, we are going to use delta H of the reaction can be calculated total of the bond broken minus total of the bonds formed. So that's a different thing, right? In this case, you actually you look at the picture and see how many bonds are broken. You are breaking only the double bond and the 1H2. That's the only thing you're going to break. And the other side, you only add 2 times of CH. So only the difference you need to calculate. You can do the whole thing, or you can just simply do the way I did. So either way, you're going to get the answer for this one, right? So you can calculate all the bonds broken. You can calculate all the bonds formed, or you can simply find out the difference. So that will give you the answer. And you can also use the formation enthalpies, plug in, and it should be close enough. In this case, 120 kilojoules per mole. This one gets you, let's see how much the value, minus 88 to minus plus 52. So that's a minus again. So it's 140. There's a minor difference. That's just because of the data sheets, right? You always have to follow your professor's data sheet and your teacher's data sheet for sure, right? And don't believe what I put there, or what is Wikipedia or somewhere anywhere else saying, depending on your professor's book, right? Data sheet. Now, so, and also I can give you another example. Look at this one. So yeah, this is the people have been asking many times different questions. So 4 ammonia, 3 oxygen gives you 2 nitrogen and 6 water. All are gases. And you are looking for the delta H of the reaction. Now, so what's the givens? The givens are this way. So these are given for each reaction. So ammonia, it's 92 kilojoules, 2 ammonia production, and then 2 water gas production is minus 483 kilojoules. And make sure there is no end kilojoules per mole. It's given per kilojoule. That's given for the reaction. Now, what you do in these cases, all these are given, so you're going to write your question again. This is what we are looking for. Write the question below. Draw a line, and we're going to do a little math here, right? Now, this one, you have 3 oxygen, so you're going to 3 times everything in the information. And the ammonia, you need 4. that has to be flipped. Flip that one, ammonia reaction, and 2 times that gives you 4 ammonia, 2 times of 3H2, 2 times of, actually 2 times of 3 hydrogen and 2 times nitrogen, right? So that's correct. So now the value also, it's -2 because it's reverse, and 2 times -2. So now actually only the 2, yeah, here, not the top one. So these 2 gives me the product. So you cancel the each side, what you can cancel numerically, and see, you have 6 water, 2 nitrogen, 3 oxygen, 4 ammonia, where they should be. All are good now. So now you just numerically add all the values on your right side. So 3 times of -483 and 2 plus 2 times of -92. So that should give you the value. So 1449 minus, that's, sorry, then minus and plus, minus times minus, that'll give me plus. So that will be, yes, it's actually final answer 1265. Let me see this bracket. It's positive 184. So then 1449 minus 1449 plus 184, it'll give you the final answer. You see here, yeah, this is the argument. So there's no divided by kilojoules per mole. Okay, that might be a typo in, if you see anywhere. It cannot be. So it definitely a typo. So I'll give you another question to try. So H2Br2 gives you 2 HBr gas. So it's similar to one of the questions I did. So delta H reaction you're looking for. And then you can do 2 ways, right? You can use the formation enthalpies, or you can use the bond dissociation energies. In this case, you need the Br to Br. It's 193 kilojoules per mole. And you also need HBr bond dissociation energy, which is, it's 363. Okay, good. Now you can, plug into the answer should be 101. Thanks.